Thank you so much for watching the Weaviate podcast. I'm super excited to welcome Weaviate CTO and co-founder Etienne Dilocker for the Weaviate 1.20 release podcast. This is another packed release of Weaviate with all sorts of cool things: multi-tenancy, PQ rescoring, AutoCut, re-rankers, a new hybrid rank fusion algorithm, and some cloud monitoring metrics. Every time we do these release podcasts, it's always so much fun. I always learn so much. So Etienne, firstly, thank you so much for joining the podcast.
Thanks so much for having me. Same for me. I love talking about these things. I love the great questions that you always prepare, and I'm very, very excited as well to talk about this one.
Yeah, amazing. Yeah, I love just like the breadth of it, going through all the different topics in Weaviate. And so starting off with, I think, just a super exciting topic, diving into the database thing, multi-tenancy. Can you tell us, maybe just to begin in the highest level abstraction, like the overview of what multi-tenancy is?
Yeah, what it is and sort of why you need it even in the first place. So multi-tenancy for us, and I always feel like I need to sort of, because when people hear multi-tenancy, they think of cloud operations, sort of shared resource and cloud operations. And of course, we have a cloud service. So multi-tenancy for us is not about how we run the VBA cloud service. Yes, you can use multi-tenancy on the cloud service, but it's actually about multi-tenancy for you, the user. So let's say you have an application, your application has separate users, and they have somehow data that needs to be separated in one way or another. So for example, let's say you build an app and your app allows you to index documents that you have on your hard drive. So maybe just sort of install something on your, let's say something like Dropbox or so. You want to search through all your documents. You only want to be able to search through them yourself. You definitely don't want other users who happen to be using Dropbox to be able to search through your documents. So that's kind of the idea of scoping that to individual tenants. So you as a Dropbox user in this case would be a tenant. Or it could be that multiple users, maybe instead of Dropbox, it would be a workspace on Notion or Atlassian Confluence or something. So in this setup, basically a group of users could be a tenant. So it doesn't necessarily have to be an individual user, but it needs to be some kind of isolation unit, basically. And this is so far, this is not even like a technical requirement. That's essentially just an application level. How do you query it? What do you have access to requirement? But then where this gets super interesting for vector search is that it kind of mixes with the technical requirements. And it's almost like it's sort of, it perfectly aligns, because in vector search, we have the problem that we need to somehow figure out how to sort of limit the vector space. And we've talked about HNSW, the sort of the indexing graph in the past. And now think of this whole graph that contains maybe 1 billion vectors, but these billion vectors are spread out over 1 million tenants. Now you would have to sort of, assuming there was no multi-tenancy, you would have to essentially cut that graph into a very small chunk that only contains about 1,000 objects each. So for 1 million tenants have a total of 1 billion objects, that's only 1,000 each. Chances are this graph becomes disconnected, or you have to travel a lot through that graph without sort of hitting nodes basically that you're not allowed to hit or that you're not supposed to hit. So this single graph and filter kind of approach is at best the workaround. Like we have this in Weaviate, we have this flat search cutoff basically, where if the filter becomes too specific, you actually do a flat search. So this would be one way to work around it. But then you sort of lose the whole benefits of the fast pace or the high throughput and low latency kind of search that you expect from HNSW. So there is a need to basically also do this kind of separation from a technical level. And this is where we said, okay, enough workarounds. Another workaround that users have semi-successfully used in the past was to separate this on a class level, because in Weaviate, a class is already an isolation unit. So you could sort of say per tenant you create one class, and they would all these classes would have an identical schema, because it's all the same use case. Basically, you just copy it for individual users. So your schema keeps on growing and growing and growing, and like each schema update made the whole thing slower and slower. And this worked okay-ish for maybe 2 to 3, maybe 5,000 tenants. And one workaround, and then really we're talking about workaround after workaround. Another one was then you could turn off GraphQL, because part of rebuilding the schema, part of what took so much time was rebuilding GraphQL. So you could turn off GraphQL, only use gRPC. That would make it scale a bit farther. But we were really in the territory of like, this is not a long-term solution. This is hopping from one workaround to another. So we said we really want a dedicated multi-tenancy solution where the APIs support tenants, where the architecture under the hood supports a lot of tenants, and most importantly, where this also somehow scales linearly. And we can talk a bit more about scaling.
Yeah, it's so interesting. I remember when I first heard the question about doing this kind of thing, I heard, I was at the meetup in New York City, and someone said, "Do you guys support RBAC, role-based access control?" And at the time, I'm thinking also that you could just have that filter through your class, where if you have like a document class and you have content, you have user and user Etienne, user Connor to only look at like Connor's emails instead of Connor seeing Etienne's emails. And so hearing about the limitation of that as if you connect a HNSW graph, the filter, it might not be connected still. So you need to modify HNSW itself. So as you were giving that explanation, it really helped something click for me is the difference between just kind of naively using multiple classes in Weaviate as we understand it. Like I have an Etienne class, I have a Connor class, I have a John class. But so could you tell me a little more about the design of multi-tenancy and how you have native multi-tenancy? And I think really to separate these two things, hopefully it's not a selfish question from my understanding, but the difference between just creating a bunch of classes in Weaviate 1.19 compared to the native multi-tenancy in 1.20.
Absolutely. This is definitely not a selfish question. I think our viewers and listeners will absolutely appreciate that as well. So this class-based workaround kind of worked because one thing that a class already does is it creates something like some separate space somewhere basically in the class. And internally in Weaviate, this is a shard. And within one class, you could have anywhere between, so this is in the traditional mode without multi-tenancy, you could have anywhere between one and any number of shards. And a shard is essentially, you can think of everything that's in the database is contained in that one shard. And whenever there are two shards and you want to maybe query across two shards, then under the hood, this is split into two queries. Each shard does their part on their own and then it's somehow aggregated again. So this is why this workaround kind of worked, because by creating 10 classes, you also under the hood created 10 shards. It was kind of doing a lot of overhead for essentially you just wanted to end up with 10 shards, but you could kind of do it with creating 10 classes. The multi-tenancy feature, the native multi-tenancy feature, in the simplest terms you can think of it, it's a single class, but within that class, we create one shard per tenant. So shards are now no longer this static thing, but they're completely dynamic. Like you can add them on the fly, you can delete them on the fly, and the kind of cluster association with a shard still holds true. So I need to explain a bit more for this probably. So in a Weaviate cluster, let's say you have a cluster of 3 nodes. Let's make it simple. Like multi-tenancy, you can go hundreds of nodes, but let's keep it simple, 3 nodes. And let's say that in our class example, you would have each class would just have one shard. A shard is something that can't be split further, basically. Like if you want to split it, you need more shards. So in that old setup, this shard with this specific configuration would live on one of those exactly 3 nodes. So one way of distributing this around the setup a bit would be if you have 30 tenants, or in the old setup, 30 classes. I mean, you would have 30 tenants, but you would model them with 30 classes. Each node could hold 10 of those, basically. And then that would sort of be evenly distributed. But you'd have very little control. Now, with multi-tenancy, we keep that idea of having one shard, but the shards have become much more lightweight. So you have essentially, we've run a couple of load tests, and we could, in one example, this depends a bit on sort of what kind of properties you have in your class and these kind of things. And essentially the bottleneck is just the file descriptor limit that Linux systems have. And one test, we could reach 70,000 shards per node. And per node is now where this sort of very interesting part comes in, because you can just scale this by adding more and more nodes to your cluster. So you would have a single class. That class potentially spans the entire cluster, but a single tenant still is isolated to one node. So this and to make this a bit more complex, we could then also add replication, because then you can make sure that this node doesn't become a single point of failure. But for now, let's just ignore replication. So you could start with a 3-node cluster. Let's say your tenants are really huge and you would only fit 10 per node. Then you could fill up to 30 tenants on that cluster. Now, if you want to onboard more users, you just add a new node, and per node you would again have roughly 10 tenants capacity. In reality, it's more like 10,000, but for our example, that makes it easier to reason about. And then Weaviate under the hood makes sure that you hit the right node. So of course, as a user, you don't know where that stuff is scheduled, but Weaviate will just say, like, with every, and this is the only real API change for multi-tenancy, is that now you have to specify your tenant key. So you don't have to use a filter. Basically, in your, let's say you do a get near text search, then you just have an additional property that's the tenant, and then you should specify that, and Weaviate uses that under the hood to figure out sort of where in that 3 or 5 or 500 node cluster, where does the tenant actually live.
So then, so I'm curious now about kind of maybe the design decisions behind the tenant key and kind of the reduction of the sharding, like taking down the size of each shard. Maybe we could step more into the technical details behind what it means to have a shard be lighter weight and dynamic.
Yeah. So the idea of splitting by shard or by class or by index type for multi-tenancy, that is not new. I know, for example, that for if you need to be GDPR compliant in traditional search engines such as Elasticsearch, you would also try to use that same pattern where you would create an index, I think it's called an Elasticsearch, per tenant, then to have that strict isolation. So that is kind of where also this is essentially our class-based workaround. But this always sort of comes with limits. So what we said is we need to make the shard more lightweight. And making it more lightweight is essentially sort of an umbrella term for all the kind of things that kept us from having sort of a lot of shards on one node. One thing, for example, is asynchronous processes. So since a shard is its own contained unit, in the past, we would have lots of async processes. So for example, for the HNSW index for maintenance, that would be an async process. For every property that's stored in an LSM store, one async process would be to switch from mem table to segment. So when a mem table is flushed, that's essentially the memory storage is then written to disk. Then you have compactions in the background. So you have all these kind of sort of background processes that tend to be relatively lightweight, but let's say you have 10 of them per shard, and now you have 10,000 shards because you have 10,000 tenants. Now all of a sudden you would have 100,000 of those backup processes. And in our very first test, before adapting anything, we could see that essentially all CPU time was now spent on just idle background processes doing nothing. And then to make this even worse, some of those doing nothing kind of processes, for example, the ones that would check for whether LSM segments need to be compacted, they did that using a disk read. So a very innocent sort of simple disk read of, hey, what is the state on disk right now? But now this happens 100,000 times in parallel, and now you hit your disk with all these unnecessary reads just to find out that you don't have to do anything. So very simple changes such as making sure, can we cache some of that information? Can we check less frequently if there hasn't been a change in that much time? Can we, sort of all these kind of can we combine internally? I think this thing is called the cycle manager, and there's one discussion that we have, like, instead of having 10 per shard, could we maybe have just one, or could we have less than one because we take that outside of the shard? So all these kind of optimizations that enable us to run more shards under the hood and essentially making them more lightweight. Another thing is also the memory footprint. So in our very first test, we had a surprisingly large memory footprint for an idle shard. Don't remember what it was, but I think it was something around 5 megabytes or so, where in a single class, single shard setup, this would just never, like, you wouldn't even notice that like you have one class with one shard and now you have 5 megabyte of memory usage. Not a lot. But now again, times 100,000 or times 10,000, all of a sudden you have this like 50 gigabyte of idle memory or not idle memory, 50 gigabyte of used memory for what is essentially idle classes. So that was another optimization. Again, sort of a very simple optimization, which is to make this more lightweight. Just look at what kind of memory, how are we allocating memory? How are we doing this dynamically? Are we a bit too optimistic about where the shard is going to grow to, and just sort of setting more reasonable defaults, making sure it can still grow. So there's essentially no negative user impact. Everything can still grow, but just the defaults are more reasonable and more aligned for having many of them. And that's kind of what we mean by making them more lightweight.
Amazing. It's such a clear explanation of it, and yeah, it's really interesting hearing about these background processes. Hearing about the compact and merge. I don't know too much about the LSM myself, but that explanation, I can understand how there would be, background processes that check on the database and that kind of thing. So, so you mentioned the, seeing the 5 megabytes of overhead per class, and kind of the insights that you gain by testing it. And I think that transitions nicely into this next question that how have you been testing multi-tenancy? And I guess it's kind of, I think what are the lessons from it? Like, it sounds like with the megabyte thing, even though you have such a deep understanding of Weaviate internals, you still learn from your tests. So I'm curious, like, how this feedback process of testing it, how exactly it's tested, and then what has been illuminated from the tests.
Oh yeah, absolutely. This feedback cycle goes sort of beyond just the test. It's user feedback. Like, I think the whole journey of getting into multi-tenancy started out with user feedback saying like, hey, I'm trying to apply these workarounds, but now I'm seeing large memory footprint, or now I'm seeing stuff slowing down, or I'm seeing my disk being hit even though I'm not querying, and these kind of things. And that was, I think, in multi-tenancy, that was the first thing that even made us aware of, hey, there is a need for something new. There's a need for a revolutionary change, basically, not just extending the workarounds. And then I think there, in testing, you could say that there were two major phases. So the first one was initially when we started out, this was in proposal phase, and we just wanted to see, like, is this a viable idea? We had the proposal out on, because we do this out in the open, of course. We had that out on GitHub, and just, it was sort of a mix of, this is why we think it's technically feasible, this is what it would provide, and just asked a couple of users for feedback and if that would solve their cases, and that was overwhelmingly positive, so that was great. So then we just did a very simple load test, essentially the old setup, which, because we knew that a shard is going to be a shard. Yes, we're going to make it more lightweight, but essentially we can already create a shard. So I think the first test, we used the class workaround, but then we also increased the number of shards per class, because our end goal was having as many shards as possible. And then we don't remember the exact numbers, but let's say it was something like 50 shards per class. And then we just kept on adding class after class after class. And at some point we would say maybe hit 10,000. And we would say, like, oh, all of a sudden the next query is now failing. And then we'd investigate, like, why are the queries failing? What is going on? And that would be part. CPU profiles, for example, seeing what do CPUs spend time on. That is when that whole background cycle sort of thing became apparent. Memory profiles, just to see, like, where is the memory actually used right now. Simple queries, sort of sending queries where we'd say, like, okay, this query in isolation should be fast, but now in this large setup, it's slow. And then sort of investigating, working backward from that, where it is. That was the initial phase where we saw, okay, what we have right now is not a good sort of, not the final solution, but we're well aware of what these problems are and how we can fix them sort of with the final solution. So that was essentially proof of concept that we're on the right path. And that was sort of, it failed successfully. Like, it failed in the places where we expected it to fail. But also it proved that if we fix these kind of hurdles, if we get rid of those hurdles, it would essentially work. And that was before we wrote any kind of line of production code. So that was basically back in, you could say, in the 1.19 release cycle, we kind of prepared for the 1.20 release cycle where we built multi-tenancy. Then came sort of a classical implementation phase. Of course, implementing that has lots of tests and everything, and we would sort of constantly try to evaluate. But also sometimes you just need to wait for it to be sort of like, for it to reach a certain level of maturity that you can do sort of these black box end-to-end tests, where sort of in unit tests and integration tests and even to some degrees end-to-end tests, you always have some kind of knowledge of the internals, but with these kind of end-to-end, really end-to-end black box sort of API level tests, you just don't know anything about the systems. You only get to use the same functionality that your user would use. And then you just try to stress it. You just try to replicate how would a user use it and see where it goes. And there was a point, I think, about 2 weeks or so before the release, when Red One from our team, I asked him sort of like, hey, what can we do right now to sort of help you, give you confidence in the release, because he took a lead basically on the whole cloud orchestration side of multi-tenancy. And he said, please break it for me. Try to break it for me. And then we got together and we tried to break it. And we found a couple of, there was no fundamental issue, but we did find a couple of things. And it was great that we found them, because I think some of them were bit on the edge case side that would have probably taken a few weeks for users to run into them. Some of them were a bit more obvious. We could find them out right away. And then we built this more or less elaborate, I would say, load test setup, where we just kept on importing, kept on querying, measuring all the metrics, like what. So the linear scaling was extremely important for us. So we wanted to make sure that if we have, say, I'm trying to use the actual numbers that we used, but I think we started with a 3-node cluster and we aimed for 10,000 tenants per node. So we'd start with a 3-node cluster with a total of 30,000 nodes. And then we said, hey, if we turn this into a 9-node cluster, and instead of 30,000, we would do 90,000 tenants, then we still have that same ratio of 10,000 per node. So everything should scale the same. Is that the case? And then we tried and we could see, and this was like one of those moments where it's like, yes, we've reached linear scaling, where we could see that the 9-node cluster essentially is 3 times the 3-node cluster. And that is very, very comforting, because then okay, now most likely the 12-node cluster is also going to be 4 times as large as the 3-node cluster, and all these kind of things. And that gave us the confidence that, hey, these claims that we make about if you want to extend it, just add more nodes, this is really true, and there's no additional overhead for, say, for import time or something, because the orchestration that needs to happen in the cluster is minimal. The node that owns the shard basically does all the work. So by adding more nodes to your cluster, you're not just adding more space, in a sense, like more disk space and more memory, but you're also adding more compute power, which can take off the load. So a very simple way of scaling import throughput, essentially just using a larger cluster. And that was the second testing phase, where sort of that gave us the release confidence. And this is something, of course, like you would do testing in automated and in manual and explorative and all these kind of stress testing, chaos testing. You do this before any release. But I think for this release, this was the most amount of testing we've ever done. So this is I would say the most confident we've ever been about a feature. And this is mainly because we knew we have stakeholders that were really waiting for this, and they're really saying like, hey, this is sort of not having multi-tenancy, or not having a multi-tenancy solution that scales to millions of tenants, is what's keeping us from reaching the next level with Weaviate, or maybe for others, keeping us from using Weaviate in the first place. So we really wanted to make sure that while we knew that there was a limit with the previous solution, like now we want to confidently say these limits are gone. You can use it for the kind of scale you want. And now essentially the only limit, that there are 2 limits. One is the number of file descriptors. So that varies a bit, and that is local to one node. So the safe estimate is around 50,000 tenants per node. Most likely you're going to run out of other resources before that. So that's the one limit. So upwards of 50,000 per node. And the other is just resources. So resources is something that that is just vector search in general. It has nothing to do with multi-tenancy. And that is also something that's easy to increase. You just add more nodes. So these are the 2 theoretical limits for number of tenants, and both are very easy to overcome because both linearly scale with the number of nodes in a cluster.
Yeah, it's so interesting hearing about the like try to break it test. I think that's been one of my favorite stories following along with Weaviate has been like, the sphere test and, blog posts about that, and, trying to get 1 billion nodes into Weaviate, and that whole like load testing thing has always been so interesting. Like I remember it's kind of like a theme of all of AI, like, like with language models, it's like, how big of a language model can you train? It's like, oh, we trained 50 billion. It's like, wow, it's so impressive. And this is kind of like our analog of that is like, how many vectors can we put into one index? And I think also kind of seeing it, across indexes and, one kind of system across the nodes is so interesting. I have a quick kind of clarifying question, selfishly for me. Hopefully,
Sure.
there is a listener with it too. So, when you're sharding a class, so I understand that each class, it's the document class, and I have a million documents in it, and I have one vector index. So when I shard this, you mentioned like searching each shard separately and then aggregating the results somehow. Can you maybe take me a little through further how you shard a class?
Mm-hmm. So here we really need to separate multi-tenancy from single-tenant cases,
Mhm.
because in multi-tenancy we use these shards as isolation units because you only want to search through one. Like in multi-tenancy, like your query is for a specific tenant, so we'd say there are 100 shards, each corresponding to one tenant. We would pick exactly one of those 100. We would have that shard serve the request, return it to the user. Nothing changed. So this is kind of the like a small portion of the data on the node is queried in isolation, and the entire query is completely sort of self-contained in that shard. If you
Mm.
shard for that case, it doesn't matter how many shards you have. Like even if you have a million shards, because you're always hitting exactly one, there's never any overhead for number of shards. Like whether you query 1 out of 10 or 1 out of 100 or out of 100,000, it's always the same. You're always querying one. But in a single tenant case, the motivation for sharding is different. So in a single tenant case, you don't have the tenant key. So the results that you expect are the entire vector space. So now your
Mm.
motivation for sharding is kind of the other way around. Like you don't want to have as many shards as possible. You want to have as few shards as possible. So for this, the question is basically why do you want to? So if it's better to have fewer shards, why do you want to have shards at all? And this
Mm.
is where sort of um, the scale of a single index comes into place with respect to the hardware that is scheduled on. So
Mm.
that was a very complex way of essentially saying like you can only fit so much on one machine, and if you need more than that one machine, you need to shard it across 2 or 3 or 4. So that is the motivation. In let's say we have an index of 1 billion objects, and each machine could only fit 250 million. Then you would shard that across 4 machines, and now, if the query comes in, all 4 machines would say, hey, okay, I'll give you the top 10 or whatever
Mm.
results out of my 250 million. So you would now end up essentially with 4 lists of each 10 top objects. Now you have to aggregate that list again. That's super easy to do because you have, let's say, the distance metric. So essentially, you just
Mhm.
resort that list of 40 and cut off the bottom 30 again. So you have the top 10 remaining. That is easy to do. But from a sort of scaling out perspective, you need 4 nodes to serve your query. Whereas in the multi-tenancy case, because only a single node owns the data for your one tenant, also only that one tenant needs to answer it, which means all the other nodes and all the other CPUs on that node are idle to serve other tenants, basically.
So when you have the HNSW graph, is there anything to how you partition? So imagine like on layer 0, I have like these are clustered, and so we're going to go shard together. Is there anything?
The shard is at a higher level, so the HNSW index would be fully contained within the shard,
Mm.
and it wouldn't even know that there are other shards. Like the shards, you can think of this like class shard, and then in the shard you would have vector index, regular index, etc. So
Mm.
the HNSW index doesn't even know that. That said, this is something I think that would be interesting for future research to see like could we shard instead of sharding by sort of an application level attribute. So right now we use a hash on the ID. You could also potentially shard by vector proximity. So that would
Mm.
be the case where sort of a bit similar to how IVF based indexes work, where
Mm.
you have these kind
Mm.
of buckets. So you could say, if I know that my data set is going to have 10 shards, could I try to sort of pre-select one of those 10 shards based on proximity and make sure that the vector sort of ends up in the shard that's closest to it?
Mm.
Problem is, what we know from IVF based indexes is with a multi-dimensional distance, it's not as easy like in a sort of, it's not a binary decision. It belongs into bucket 1 or it
Mm.
belongs in bucket 10. So in IVF, what you need to do is you still need to query multiple buckets, like let's say out of 100 buckets, you still need to query the top 25 closest. So that's a like interesting for research, but currently that's not something. So currently the shard is at a higher level in a single tenant sharded setup, and the vector index within that shard wouldn't even know that other shards exist.
Hmm. Yeah, it's really fascinating thinking about the, like the vector indexes and then how you distribute vector indexes across cloud computers across the world. And this it's all really exciting. I think kind of we're transitioning into this like, future improvements, future works topic broadly. I hopefully we didn't go too into just sharding particularly, but like back into the multi-tenancy, like do you see, what are some things that are top of mind now that rolling it out?
Yeah, there's one aspect that I haven't even mentioned at all yet that I'm super excited about. What we wanted to achieve with 1.20 was we wanted to have a stable API, we wanted to have sort of the main functionality, which is scale. So anyone who was blocked by not being able to onboard or to get started with Weaviate because of lack of multi-tenancy features, we wanted to say like you can get started with 1.20. But this is not where multi-tenancy ends. Basically, this is basically just the beginning. And one big sort of potential for improvement that we have is cost reduction, because something that if you have a multi-tenancy case, most likely not all of your tenants are active at the same time. If they are, all your tenants would need to sort of be active. And this is, I'm using this fuzzy term of active versus inactive, because that's that sort of, yeah, just as an abstraction. We can go into what that means as well. But if we say that we have active tenants who are potentially expensive, like let's say they need a lot of memory, they need a lot of compute, and we would have inactive tenants which are not expensive because they don't need memory, or they would need the memory at the moment that they become active, but in their inactive state, they would use fewer resources. Now, what that allows us to do is potentially size Weaviate cluster for the number of active tenants as opposed to for the number of total tenants. So if you have, let's say, 100,000 tenants, and you would say that your infra bill for 100,000 tenants is $1,000. If you know that only 10% of your tenants are active at the same time, and you have a way to deactivate those other 90%, you could reduce your infra cost from $1,000 to $100. And this is where it gets really interesting, because as the cases grow, like in vector search right now, almost all cases are always sized for data set. Like it's always the first questions like, how large is your data set? What's your dimensionality? How many objects do you have? Maybe can you use compression? What are your query requirements, etc. But kind of the cost is linear to the number of objects. But with multi-tenancy and the ability, and this is sort of what's coming next, the ability to deactivate, and then there's more things sort of in the pipeline beyond just deactivating them. But just with deactivating them, we would not need any memory for those tenants anymore. So if you can say that even if it's just 50% or so that are inactive, you would essentially have twice the number of tenants, or could host twice the number of tenants on the same hardware. And this is where I see a ton of potential for even more cost saving, because realistically there's always this like long tail distribution where you have a few tenants that have a lot of queries, and a lot of tenants that maybe query once per minute or once per hour even, or maybe just once per day. And you can potentially serve them from much cheaper hardware, and that makes it way easier to reduce operating costs with multi-tenancy.
Yeah, that is really interesting hearing the like the prioritization of certain resources and so on. And I just kind of was having this epiphany about how this could help. Like if I'm building a machine learning app with Weaviate and I'm collecting user data, I'm thinking about I just kind of unlocked in my brain how much this multi-tenancy enables. Like just as a random example, our last Weaviate podcast was with Alexa Gordich from Ortis, and if I'm collecting the user data of everyone interacting with his YouTube chatbot, I have this new multi-tenancy way of collecting that data and feeding it into my machine learning system. And yeah, just incredibly exciting as I'm understanding it better from hearing you speaking about it.
Yeah, also makes it easier to get the data out for a specific tenant, because essentially like a a list all query is now
Mm.
specific to a tenant. So you're now listing all the data for that tenant. So
Yeah, so I guess like when I was first thinking about this topic of multi-tenancy, I hadn't understood the just users with the same kind of class well. Hopefully, I'm making this like I thought about it like say I want to have all these different classes with different properties. Like for whatever reason, Connor has a age property, but Etienne, I don't know, you just have like a hometown, like what I'm trying to say is like different properties or like different
I'm
vector.
ageless.
Picked a good example. Yeah, like I guess I was thinking like, especially with the vectorization configuration, I think maybe, like different classes would vectorize a different property and stuff like that. But yeah, I think just, having, millions of users for the same kind of class, that application makes a ton of sense. And yeah, it's just really, really exciting stuff. Awesome. So I think that's kind of a roundup of multi-tenancy. Etienne's written this incredible blog post in addition with the Alice Corp and Bob and Corp, I like the examples. And so, release post, release notes, all this cool stuff. So awesome. So pivoting to our next topic, product quantization. I think this was first released in 118 or 119. A super clever vector compression technique. I think the history of Weaviate, you first started exploring vector compression with binary passage retrieval, where you're like hashing, positive and negative of each vector dimension. But the problem with that binary passage retrieval, I think, is you really need to train with it. It's not really something that you can do with vectors that just come out of the box from whatever model. But this product quantization thing where you cluster the values and then represent them with the centroid IDs, you can apply that to any kind of vector. And so it's really universal way to compress vectors and just overall really exciting way to kind of reduce the memory required in these vector indexes. Yeah, could maybe start broadly on like where is your head currently at with product quantization?
yeah. Yeah, as you said, we initially released this, I think 2 or so releases ago, 1.18. And we slapped this experimental label on it. And that was not because we didn't trust our implementation. That was because we said, we're gathering feedback. We want to see how do users use that? What can we potentially do to improve it? And we were well aware that this could come maybe with some API changes that in the sort of regular semantic versioning API guarantees we couldn't uphold. So they said like, hey, this is experimental. This is probably going to change. Maybe not, but this is kind of the evaluation phase. At the same time, we don't want to keep it from users. Here you are. Here, please do use it. Be aware that either it would change or maybe don't use it in production yet unless X, Y, Z. And that also in turn meant that at some point that experimental phase needs to end and it needs to become generally available. And that is now with 1.20. And that's the one big change. Just in general, we incorporated all that feedback of sort of maybe it wouldn't work as expected in some cases. Maybe there are ways to do things better. Like that is one part of where we're at with PQ right now. But then the other part is also we've improved it. We've added what we call rescoring, and this is a very simple change that has a massive impact. So in general, PQ is a lossful compression. So you reduce the number of, let's say, standard example, you have a 768 dimensional vector. With PQ, you would represent 4 dimensions, or this is configurable, but let's say, for example, you would represent 4 dimensions with a single byte. So now what you have is previously for those 4 dimensions, you used float 32s. So that was 16 bytes. And now you not just do you reduce this sort of from float 32 into just a single byte, but also you pack multiple dimensions into a single byte. So in this simple example, you can reduce the memory footprint for 786 dimensions by a factor of 16. So that's extremely sort of that's an extreme improvement. But at the same time, if you do that, your recall would drop considerably. Like you would your memory requirement is a fraction of what it was before, but also your result quality is bad now. So what we said is, well, but we're still using PQ in combination with this HNSW index. And in HNSW, essentially, you have a top K heap. So you have like a temporary list of what you think is the current results. And while traversing the graph, you sort of keep improving upon that list. And the final result is essentially the result that we pass to a user. So that's a very simplified explanation of how search results are gathered within HNSW. And that means that if we use that compressed PQ distance to make a decision of whether we want something, basically whether we want to add it to the list or whether we want to drop something because the list has a fixed size. So whenever we add something that's a worse result needs to drop off. And if we do that based on the compressed distance, oftentimes that decision is wrong. And then this sort of small compression error would accumulate more and more and more. And in the end, you would have a lot less recall. But if occasionally we actually load the real vector from disk and use the real vector to make that decision. So this is the rescoring part. We actually take the original vector from disk. So now you're trading a bit of performance. You have a disk read now, where previously you wouldn't have a disk read. But in exchange, you now get way more accurate results. And I think we have a blog post coming up in a week or so, or maybe two, where we have some graphs in there. And it's super exciting because in some cases, the recall QPS trade-off, sort of these curves where top and to the right is typically best, is actually not any worse than it is with uncompressed. So it's like you don't lose anything. That's not true for every case. Like in some cases, there is still a bit of a trade-off where you can essentially say, like, am I optimizing more for efficient storage or am I optimizing more for efficient querying? But in many cases, it's actually not a trade-off anymore. You just need to turn it on. And this is in turn a bit sort of depends a bit on how much memory you have available in general, because just of the way that operating systems work, like a disk hit only makes it to disk if that portion of the disk hasn't been cached in memory before. If there is memory available, the operating system, so that's the page cache, will start caching portions of the disk. So what is technically a disk read might actually not even be a disk read if you still have some memory available. So you get these like buffer zones in which the performance is still great, even though the memory usage has dropped a lot. And this is the second feature for PQ that we said, like, okay, once we go for general availability, want to have that in. And now we're at a point where previously it was like, use PQ sparingly in some cases because it reduces your recall. Now it's more like, why wouldn't you use PQ? Please, everyone, go out and use it. It's awesome.
Yeah, I think when I first heard PQ rescoring, I thought of it in the re-ranking way that we'll talk about next, where it's like, you get the top 100 results with the compressed distances, and then you just kind of bring the full precision to just re-rank. I didn't realize how deep into the HNSW traversal, how, say, I am still like curious. So you're like exploring the neighbors of the center node, and you're going to kind of like resort the candidate. I think maybe, I don't know. I think it's maybe outside of the scope of the podcast, but like just, understanding that HNSW has this like candidate list and dynamic nearest neighbors, and you like rescore it to have a better search, like deep into the traversal rather than just at the very end. I think that part. Yeah, that's like the elegance of it. So I have kind of two questions I want to ask you about PQ. The first is maybe a clarification of the in-memory on disk part of PQ. So I'm curious if this is the correct understanding. So, we load, say, 200 vectors into Weaviate, and now we trigger PQ. We fit the k-mean centroids. So from then on, a new vector comes into Weaviate, do we just send the full precision vector to disk, and then the compressed vector that goes to memory?
Exactly. Yeah. So we always retain the full vector basically on disk. Like you store what the user provides, which is the real vector, so to speak. But we also compress it and then only keep the compressed one in memory. Additionally, we also need to store the compressed one in memory. So if the server restarts, you don't want to recompress everything. So we store both actually. But exactly as you say, initially we keep the original on disk and keep the compressed in memory.
Fascinating. I remember one of my takeaways from when we met with Matthias Duze from Meta, who's one of the pioneers of product quantization, was this like online k-means kind of problem, and thinking about like, how many vectors do you need to load in to compute the centroids, and then how does this scale with incremental updates? I guess the question would be like, what are you kind of learning about that problem?
Yeah, you need a certain, so it's very hard to pick an exact number because you need your data or that subset of your data needs to somehow be representative of the entire data set. So in the ideal case, let's say you would have 5 clusters in your data naturally. Then those
Hmm.
5 clusters, and then you want to train on 10%, then those 5 clusters need to be represented in your original 10%. If they're not, for whatever reason, like if let's say the fifth cluster didn't even exist and you only have 4 clusters for training, then you're training on something where the fifth cluster doesn't exist yet. So that doesn't mean the fifth cluster can't be assigned anywhere, but it means
Hmm.
the sort of trained model isn't as good as it would be if that had been part of it. The good news is that there's a certain size where it gets more and more likely that the distribution of the data set sort of doesn't change. Of course, that's no guarantee. Like it could completely change. Um, but often what we see, so for example, on these ANN benchmark data sets that are typically between 1 and 10 million, I think we typically didn't see any improvement when
Hmm.
using more than 100,000 vectors
Hmm.
for
Hmm.
training. So that's still a very manageable amount. I think it takes 10 seconds or so to train with 100,000 vectors. Um, yeah, sort of a good trade off.
Yeah, fascinating. And yeah, that 100,000, just like getting a sense of that is something that I think is a really interesting research question when you're, going into the details. And yeah, I think this whole like cluster analysis is definitely a lot to it. I remember, earlier we did a podcast on BERT topic and we were discussing like what would cluster analysis and Weaviate look like. I think it's starting to see, I don't want to give away, I know that we have something planned, but like, we're seeing partners, integrations, other technology companies building further into this like embedding space visualization, topic modeling, cluster analysis, and definitely people listening be on the lookout because there's going to be some really cool stuff around that coming soon on embedding drift detection and all this cool stuff. Yeah, awesome. So I think that's a great coverage of the PQ rescoring. I think probably for me the biggest takeaway is understanding how deeply that goes into the HSW traversal, and what you said I think is a huge point about originally you were thinking I'm trading off memory for accuracy, but now that you have this rescoring, there's no trade-off, so just use it. That's kind of a funny takeaway.
Yeah, yeah. For some cases, I mean, there is it's engineering, so there's always trade offs, and it's kind of like not seeing our users' data. It's hard to make predictions, but we're trying to model real life data usage with as many different data sets as possible.
Hmm.
And I'm really surprised to see sort of how good it is in some cases. Like, yes, in some cases there is still a bit of a trade off, but in others it's just not.
Oh yeah, yeah. I think having all these diverse data sets is such an interesting thing of machine learning generally. Like the variant is still kind of no free lunch in a way. Like
Yeah.
you're not gonna have.
Yep.
Yeah. Awesome. So I think kind of we have a trio of new features I'd like to kind of cluster into one kind of category, which is kind of like Weaviate being feature rich for search. Like vector search, obviously, like search relevance is a huge topic. And I kind of just to give a quick TLDR of each of these things. The first of which is re-ranking, where, so as I mentioned with my original understanding of PQ rescoring, re-ranking is this idea where you take your top, say, K100 results from vector search, and then you're going to take each of those candidates in the query and pass each of those as input to a high capacity scoring model. So where do these scoring models come from? Sentence Transformers has 6 of them that are open source, and so we've built the Docker image where similar to text to vec transformers, you have this like local image if you wanted to spin it up on your laptop, host it yourself, and all that good stuff. We have the cross encoders that have been trained from sentence transformers are up there. And then also really interestingly, we have a re-ranking endpoint from Cohere. And obviously our friendship with Nils Reimers, you've seen Etienne and Nils Reimers together. This is an API for a re-ranking model. And I think that's quite fascinating. I don't think there's another company doing that. And it's pretty interesting to see that API. And it comes into like Weaviate's module system, how we have these this orchestration of API requests. I think it's quite fascinating. Maybe actually, Eddie, and we could take a pause. And I really wanted to ask you this question about how I think an interesting thing about Weaviate's module system is how Golang handles these like concurrent HTTP requests. Maybe talk a bit about like what goes behind that, how Golang is optimized for scaling this kind of orchestration to model inference, because I think it's such a fascinating part of Weaviate.
In general, Go is a language, as you say, sort of easy, simple concurrency is one of the building blocks of why you would use Go. So Go has channels, and it has simple synchronization primitives such as mutexes and these kind of things that you need for easy concurrency. It has a race detector, which is also a super important feature to figure out, like, are you doing your concurrency safely, or are there any kind of risks? So in general, sort of Go is a good, I would say, it makes it relatively easy. And then what that allows us to do is, if a user just gives us sort of a bulk data thingy, like a batch of data objects essentially, and our job is to say vectorize them, or also re-rank them, and when to pass them to the model. If we would do that sequentially, that would also mean that whatever the latency is for one of those requests, we would be bounded by that. But the kind of cool thing about these serverless applications is that they tend to scale way better than that. So if you hit them concurrently, that allows you to sort of not have to wait for one thing to be finished, but just do multiple of them at a time. That said, again, there is a bit of a trade-off, because often these models have rate limits. So I think something that often pops up in our support forums, for example, with OpenAI, the default rate limit is, I don't know what it is, but it's something like, I think maybe 60 per second or so. That so 600 per minute. So if you want to vectorize more than that, you could potentially hit the rate limit. So also, concurrency is not a free lunch here, but it helps to at least sort of max out whatever the model provider can use. And this is the same for if you self-host your model. If you don't concurrently do something, and it doesn't necessarily mean that it has to happen with concurrent HTTP requests. That could also mean that you bulk this up into a single request, and then maybe the concurrency happens on the model side. But in general, you want to sort of not have idle capacity around. Like if there are either GPUs or CPUs that are used for model inference, you want to make sure that they're maxed out, and that is one of the motivations for using concurrency in that case. And then sort of taking that back to Golang, it's a language that makes concurrent programming rather easily. I know that some of our team members sometimes hate Go for it, because it's not perfect in any way, but no language is. But it's a very good sort of fundamental concurrency kind of model.
Yeah, fascinating. I think also like the like like our generate module with OpenAI, Palm, and Cohere. The way that particularly the way that it parallelizes doing the single result call, I find a ton of use in that, where you want to put a prompt of each of your search results and have that all be parallelized. It's so much faster than looping through it.
Yeah,
I think it's pretty cool. So. Okay, cool. So on this topic again of search results, so we have re-ranking now, where you can get better search results, and kind of building it right into Weaviate is why we took this tangent into the more technical thing. You don't have to have, manage some other service of your own to do re-ranking. It's built natively into Weaviate, and, taking that search result slice and sending it away. So the next cool thing is AutoCut. So AutoCut has this high level motivation of, how many search results are relevant. If you search for, I've stolen Bob's landmarks in France thing. I use this all the time now. So if you search landmarks in France, and you have the Eiffel Tower in Paris, then you have some other things, and say you only had like eight landmarks in France in your search result, cutting off that 9 and only showing 8 results. This is incredibly interesting for the language model retrieval augmented generation thing as well, because the language model can be quite thrown off by these irrelevant results. So like if it sees something about Spain, it might write about that because it says based on the search results, and it's like, well, it's there. So, so I think the interesting thing about AutoCut also is understanding how that's done. So it's like it's like calculating the delta in the slope from the point. So you take each of the distances, and then you have to interpolate a line from there, and then you measure the steepest change in the slope. So what Weaviate users will see is a hyperparameter on which of the steepest slopes, because you have like 2 to 3 as you traverse up the thing. So it's like, how extremely do you want to be cutting it? And then the last thing is, one of our favorite topics is this kind of rank fusion algorithm. Weaviate has built-in BM25 as well as vector search. So what that means is you end up with 2 lists. And so, the first time we did this, we were just doing, just combining it based on the ranks. So, if you're like first ranked in BM25 and like 4th ranked in vector search, that ends up, just purely based on the ranks. And now we have like a relative score fusion. So Yeah, I think all these things, just all this new benefits in search. I think the question I'd like to ask you, Etienne, is just kind of where your head's at on, yeah, like the search stuff. I think, maybe Berlin buzzwords. There was some discussions on the search side of things. I've been to the Haystack conference personally and seen that kind of like, world around search relevance.
Yeah, to me, this is as someone who's very use case driven. This is for me extremely important that we think of these use cases. And search is a big one. It's not the only one. There's recommendations, there's classifications, there's just called of course the whole generative AI part, but generative search then also is a part of there. And for me, it's I like being able to give our users something that they can use end to end, where they can say like, hey, I want to spin up Weaviate. I want to have the data management part. So you want to have the whole database. I want to have the vector search, obviously, because that's the whole reason of using Weaviate as opposed to, say, traditional search engine. The hybrid part, that's such a big one. Just the BM25, like not having to spin up something else that does the BM25 for you, but being able to do that. And then all these new additions and re-ranking and AutoCut, these are just sort of the most recent ones, but I think there will be way more down the line. And essentially, if it makes your search experience better, then it's something that we could potentially extend Weaviate with. And because of the module system, we're very flexible in even adding sort of things that essentially the module system allows us to add things that not everyone needs without bloating Weaviate. Because if you don't need the module, just don't turn it on. So this kind of, yeah, everything that makes search easier to use, better, and I guess in a way also more accessible, because there's stuff like information retrieval is like this whole research topic out there, and there's specialized conferences. You just mentioned Berlin buzzwords, which are super fun for us, but for someone who just wants better search, maybe they're not. Maybe they don't want to get into the nitty gritty details. Maybe they just want to have better search. And there we're always trying to find that balance of making it easy for someone who's new to the space without sort of taking away the flexibility that someone who's more experienced needs. And I think these new re-ranking modules and then AutoCut, these are great examples, because if you have, let's say you have your own complex ranking pipeline that's way more complex than something that you could fit into Weaviate, just don't use the re-ranking module. But for someone else who's already using Weaviate and maybe doesn't have a complex pipeline, says like, hey, there's something that I can just turn on with a single flag and it makes my search experience better, by all means do it. That's what we're here for.
Yeah. I think there are so many interesting tricks from the information retrieval community we can get out of it to get better search. I think with re-ranking, to maybe stay on it a little more, I think maybe some of the search zealots would be a little bit saying, I still can't do symbolic re-ranking. Like if you're searching for products, you might want to have the price and the relevancy, these as features that you would put into re-ranking. So you've seen we've had a podcast with MetaRank with Roman and Siva where we're thinking about this thing as well. It'll interface very similar to this re-ranking with coherent sentence transformers. We'll just send the property to the API as well, and it'll look super similar. There's also a pretty interesting discussion around like multi-valued vector search. Like I have a title vector as well as a document vector. So we're looking into all these things, as well as like the large language model re-ranking thing is quite interesting, where you prompt it with kind of the symbolic rule. So like, please boost it if it's recent, and then you give it the result with like JSON dictionaries, and that does work pretty interestingly. I think it's also really exciting for our integrations with like Llama Index and LangChain and semantic kernel, and it's a big list of these things, but I'll just leave it there, about how you can just get better search results by just taking these things on. And yeah, I think also maybe just before graduating to our last topic, I also just want to thank Dirk for this. Dirk did an incredible job with, the rank fusion and the AutoCut. I remember like the AutoCut, I was trying to figure it out myself, and it was such a headache trying to figure out how to do get the go num thing to do the slope interpolation. And I had showed it to Dirk, and he was just like the next day, like, oh yeah, here's the notebook to test it. I was like, that's so fast to turn that around. So really impressive stuff. And yeah. So awesome. So kind of our last topic is the cloud monitoring metrics with the Prometheus. And I'm curious, I imagine as you do, we mentioned like the trying to break it testing with the multi-tenancy. I'm curious like where your head's at with these, how you basically observe this massive thing running in the cloud, right?
Yeah, it almost feels like one of those boring features compared to all the exciting features that we just talked about. But I think this is what's so important to pay attention to the boring stuff, because even something like multi-tenancy, I mean, we're super excited about it, but in the end, you could argue, like, from a AI perspective, this is a very boring feature. Like, it's not a new concept, but these are the kind of features that you need to run reliably in production. And for me, anytime we add something like that, and we sort of expand on the observability stack, like, this is a simple change. Essentially, it allows you to track your success query rates. Like, previously, you could only monitor, I think, latency, but now you also get just a ratio of what queries have succeeded versus what queries have failed, and the failure reason. So was this a user initiated failure? So in HTTP status codes, this would be like a 400 plus status code. Or did something go wrong in Weaviate? So a 500, so internal server error and these kind of things, and the ones from out there. So adding the monitoring for this to get better observability basically on these kind of things. It's very boring, but it's very essential. And I love seeing Weaviate grow up and have our users ask for these boring things, because in the end, boring is production, and production makes our customers money, and that makes us happy. So it's always a place in my heart for the boring features.
Yeah, I think. Well, yeah, I think. Like, just for me, learning about like Datadog and learning about these companies that have built around that kind of thing is really fascinating. Yeah, I mean, to me, it sounds like kind of like insurance on your thing that like your data's up in the cloud. It's a super abstract concept of like a little bit of it is in Virginia, a little bit of it is in Germany. So yeah, all that is.
Yeah. Yeah, Datadog is a massive company, so that just goes to show, like, how much need there is, or how much room there is for these kind of observability topics. And it's exactly as you say. It's like insurance, it's early warning, it's just sort of looking into that. The more complex that your system grows, you can only see so much from the outside, and sort of getting these insights and just seeing what's going on can help sort of in hindsight for debugging cases, like what was going on. But ideally, before something happens, like early warning systems, like simplest thing, monitoring for memory usage or something. Like, you see something goes up nicely in a linear line, and you know that there is a certain limit with your capacity. If it says 30%, maybe that's fine. 50%, maybe that's fine. If it's approaching 80%, maybe you want to change something about your infrastructure. So yeah, these kind of operational things that you need. It's for me, it's just such a positive sign of, like, hey, people do need them, which means they're doing serious stuff with Weaviate. So I'm very happy to always ask our team to prioritize some observability features.
Yeah. Well, Etienne, awesome. Thank you so much for another release podcast. Multi-tenancy, PQ with rescoring, re-ranking AutoCut, new hybrid rank fusion, and then new updates to the Prometheus cloud monitoring. All so exciting. And then also, you can join the community Slack if you need help with any of these things. Everyone's always around and checking that all the time. And yeah, thanks so much for listening.
Thanks for having me. Had a blast. Thank you.